Alrighty. Let's dive into covalent bonds a little bit more detail by thinking about something called electronegativity and bonds being polar. Our big starting point here is to remember and to note that electrons are not always going to be shared equally in a covalent bond. So sometimes, and actually most of the time, they're not equally shared. And so this is going to, we're going to get a little bit about how we can deal with that in terms of bonding. Um, Want to point out bonding is a continuum. There's a spectrum of bonding. Okay. On one end of our spectrum, we have things that are nonpolar. A lot of times this is referred to as a pure covalent situation. This is the least polar scenario. I don't know what that says. Okay. This is the least polar scenario. Typically, this is when the two atoms are very, very similar. We'll get into that as we go. On the other end of the spectrum is ionic stuff, right? This is the most polar situation. Here we have full on, somebody's a positive charge, somebody's a negative charge. Those electrons have been transferred, okay? In the middle, we have a polar case. This is unequal sharing, okay? And when we think about this, this is atoms that are still covalently bound, so they're kind of sharing, but they're not sharing evenly. So somebody is being an electron hog and holding on to the electrons more than the other one is. And so we end up with having what we call partial charges, which we would say, partial positive or partial negative. And we'll see these again in a second. Okay. So want to think through it. One of the best ways to think about this bonding continuum is the idea of a tug of war. Okay. And oops, let me come back to that in a second. Okay. Being that the two atoms are trying to hold on to two electrons and each one is pulling them away. They want to have the electrons to themselves. They don't really want to share. They want to hog them to themselves. Okay. If they're both pulling equally strong, then we have something nonpolar. If one is way stronger than the other one, then it's going to pull the electrons completely off and we'll have an ionic case. And if it's pulling, but they're not equally strong, but one is not super strong, then they'll pull off center, but they won't fully separate the electrons out. Okay. This measurement of how much an atom will hog the electrons is known as the electronegativity. Okay. Eventually, we say this is the ability of an atom to pull electrons in a covalent bond towards itself. Okay. And when we have a polar covalent bond, electrons in the bond spend more time near the more electronegative atom. Okay. So we're going to have to worry about how do we know what's electronegative? I dropped a paperclip somewhere. What's electronegative and how different electronegativities are, because the difference in electronegativity is going to lead us towards figuring out what the polar bonds are as we do this. Okay, this is Linus Pauling, and he put out a scale he studied a lot of bonding stuff. He won a Nobel Prize in the 30s, I think, and he's the one that put out a big scale about electronegativity. This is just another periodic trend. So this is called the Pauling electronegativity scale because he came up with it. It's kind of arbitrary. It defines that fluorine has an electronegativity of 4, and then everything is ranked according to that. I don't care about the numbers, okay? What I care about is the trend. And our big point of the trend here is to say that fluorine is the most electronegative element, okay? Everything else is less electronegative than fluorine. Fluorine is the most hogging of electronegativity. So things that make things really electronegative are things that are atoms that tend to be smaller and also have a high electron affinity, right? So that's why we notice a lot of these nonmetals, right, up in this corner. is where we have our high electronegativity stuff. Fluorine, chlorine, oxygen, bromine, nitrogen. Those are really electronegative elements. Okay. Uh, Mostly because, they're hogging those electrons. So we're measuring the hogging of the electrons. Okay. But it's important to know the trend. And this is one of those things I always tease people or tease students and say, like, you know what, if I run into you at the store 20 years from now and I ask you what the most electronegative element is, you need to be able to tell me what that is, because this is an important idea. And then just remember that the trend is the farther away from fluorine you are, the less electronegative it is. Okay. Notice there's kind of an outlier in here in hydrogen. Hydrogen, you can think of hydrogen being over here. Hydrogen and carbon are roughly the same in terms of electronegativity. Okay. All right. So polar bonds happen when there's a difference in electronegativity. Okay. I didn't make these cartoons. I found them, but I love them because they're using the the tug of war model that I like so much. Okay. Um, so a nonpolar bond, we said this before, it's a least polar situation. This is equal sharing when we do stuff. Um, it's approximately no electronegativity difference, right? They're the same things. Everyone's pulling the same uh, way, and those electrons stay in the middle, and everyone is happy to call them shared. Okay. In the ionic case, there's a vast difference in electronegativity. And so one atom is pulling the electrons completely off of the other one because it's so electronegative. The weaker atom is not being able to hold on to those electrons. So those are really far apart. Okay. In the middle case, okay, we have polar bonds. They're covalent, they're pulling, but there's a moderate electronegativity difference. And so one atom has more control of those electrons than the other one does. And HCl is a great example of that. The hydrogen can barely hold on. The chlorine has got the electrons way up close to it. Okay. Um, so there we go. Okay. One way we can express this idea or note this idea is by thinking about something called the dipole moment. Okay, this is a way to picture the polarity of a bond. You can actually calculate the dipole moment. This is an energy force that's in there. This is called uh, mu, Greek letter mu for the dipole moment. We're not going to worry about calculating it. It depends on the charges involved and the distance between them, like most things that we've talked about. What I want us to be able to do is, can we draw a vector arrow, and can we identify what the partial charges are? Okay, so two ways to do it. So I got two HFs up here, so you don't have to see me draw those dudes. Okay, when we're thinking partial charges, right, we want to identify, first off, we have to identify what's more electronegative. And this one I kind of made it easy for us because fluorine is the most electronegative. So the fluorine side is the more electronegative side. Okay. Because fluorine is more electronegative, that means the fluorine side is partially positive. That's a Greek lowercase delta, means partially positive or a little bit positive, or I should say negative. This is kinda negative. Okay. On the other side, the hydrogen then is partially positive, and we set up this differential because those electrons are closer to the fluorine. Okay, because they're closer to the fluorine end is more negative, the hydrogen end is more positive. So we have a kind of negative end and we have a kind of positive end. Okay, this is one way to do it. If we're drawing partial charges, you can just put a partial positive, partial negative. You use the lowercase Greek letter delta to do that. You can also draw a dipole moment arrow. This is like in physics class when you're drawing vectors. Okay, you're going to start on the end that's more positive, and we start by making a plus. Okay, and the arrow itself, the vector, points towards the negative. Okay, so we have a positive on one side, I'm making it worse, and we draw towards the negative on that side. Okay, um, I know for me, I'm going to have you draw dipole moment arrows because they look nice, and it's a good way to figure out some other stuff because we will circle back to this as we do it. Okay, all right, something we got to be able to do. Can we rank these dudes? Can we figure out uh, which is the most polar and which is the least polar? Okay. We're not really going to be able to rank all these because two of these are very close together, but we can pick out the highest and the lowest. Okay. So if we look at this, the most polar situation is going to be the ones that have the largest difference in electronegativity. You don't have to know the numbers. Just think about on the periodic table, which atoms are the farthest away from each other, right? Fluorine being the most electronegative and going lower from there. So if they're physically far away from the periodic table, then they're likely to have a very large difference of electronegativity. Okay. Oops, come back. So the farthest ones are sodium and chlorine. These guys are going to be the most polar, right? This is actually ionic. And so that's something I want us to get into the habit of thinking of. In our bonding continuum, we say ionic, but if we're ranking things that are polar, it's the most polar situation. You literally have two separate charges, okay? In the least polar situation, okay, think on it for a second. Remember, we want things that are closer together on the periodic table. And here, that's going to be these guys. Oxygen, chlorine is the least polar. Okay, this is sometimes is not super intuitive because oxygen is very electronegative and the chlorine is very electronegative, but they're both very electronegative. And so there's not a big difference. There's a small difference between those two. Okay. As far as the other two, if you actually look at the Pauling numbers, carbon and iodine are very, very similar. So CCl and ICl are going to be roughly the same, and they're going to fall in between these two extremes as we do it. Okay. I got one more thing for us to do here. All right. Draw a dipole moment vector on the following bonds. Okay. So we have these bonds here. We want to draw a dipole moment vectors. We have three options here. Well, we're going to do all three examples. Blah, blah, blah. All right. So we have carbon and fluorine. Remember, what's the most electronegative element? Fluorine. So our dipole moment vector should start on the carbon and point towards the fluorine. If we look at O and tin, oxygen and tin, okay, which of these is more electronegative? Okay, oxygen's further up and further to the right, so oxygen is more negative. So we can point towards the oxygen. Okay. If we're thinking about hydrogen and carbon are very, very similar. Hydrogen and carbon is one of our non-polar cases. And I just realized I forgot to stress something. So there's no dipole moment vector for this. I'm going to label it as non-polar. Okay. This is the end, but let me flip back to something real quick here. I knew I left space here for something. Let's see the right color. Things that are non-polar, the best way to know polar versus non-polar and be able to identify them quickly is to say that the only true things that are non-polar are when two atoms are bound together that are exactly the same, like our HH example here. If we had Cl, that would be non-polar, right? OO, non-polar. They're two of the same thing. It's literally a difference of 0. The other scenario is HC, hydrogens and carbons. There is a very slight electronegativity difference, but for all of our purposes, those are going to act as nonpolar. Okay, when they're nonpolar, we don't need to put the dipole moment vector on them. We just label them as nonpolar and move on. They don't have any, I don't know what I was looking for. They don't have any effect on the whole idea of polarity about what's going on. Okay. Again, if you need me for anything, let me know. I can always check my email or have questions, and I will catch you next time.